Okay, so before lunch, I gave you an example of a phase field method where, not a phase field method, a sharp interface approach to looking at stresses around precipitates. And what I'm going to do now is to develop a method for adding elastic stress to a phase field method. So again, we're not dealing with plastic stress. This is strictly elastic deformations here. I want to make sure that there are no dislocations present in the structure. And to motivate, what we're doing is, so what we're going to do is to remember when we were looking at this morning, when we were looking at this beta phase particle embedded in alpha, and we said that this beta phase particle had a misfit, which was EIJ, and a misfit EIJ that was epsilon delta IJ. And so the lattice parameters differed from the alpha to the beta matrix. Now we're going to consider the case where there could be a strain, and it's going to be driven by composition gradients or composition instead of lattice parameter, or instead of crystal structure, and it's going to look like eta, where eta is 1 over A, where A is a lattice parameter. So this is the simplest kind of strain that you can imagine due to composition stresses. It's again purely dilatational. You know, it's purely dilatational because you have a delta function here. It's diagonal. And what it says is that if the composition C differs from some reference composition, you're going to generate a stress. And this kind of a model came out of the spinodal decomposition world. It was basically written down in John Cahn's original spinodal decomposition paper. And but it has far broader applications than this. And so we're going to touch on spinodal decomposition again, just as an application. But I also want to keep in the back of your minds that this model can also be used to do this problem on the left-hand side, and it can also be used on this problem. And the idea here is that instead of focusing on the difference in lattice crystal structure as you go across the boundary, you basically concentrate or focus on the composition. Composition looks like this, right? So the composition changes. And so now if you go back and you look at this term over here, you can say, well, if C alpha is equal to if C0 is equal to C alpha E, there's no strain in here. And if C is equal to C beta E, which is composition in here, you have C beta E minus C alpha E, and you get a strain. You get an eigenstrain. So you can use it to do this problem too. So, but in the context of a phase field model, it's not going to be a sharp interface. It's going to be some sort of diffuse interface that goes from one particle to the next. And so this model here on the right, over here, that we use for spinodal decomposition has implicitly in it the machinery necessary to do inclusions. And that's very nice, because a lot of these inclusion problems, where they're not simple spheres or ellipsoids, even the ellipsoid you can do, but it's not easy, and especially for anisotropic systems. But if you want to do arbitrarily shaped particles, you just need arbitrarily shaped composition profiles, okay? So that's what's really nice about this method. And so we want to go back now and write out a phase field method where we account for strains that look like that. Okay, questions? Everyone get the idea? Yeah, please.
Suppose if you have an arbitrarily shaped particle, then inside the particle the composition will be equal to C beta, right? And that means the strain also will be a constant inside the particle.
The eigenstrain is a constant inside the particle. The strain isn't necessarily a function. Okay? Yeah, that's a good point. Remember when we wrote down, for example, when we wrote down the elastic stress. Here, what we're going to do is the same thing. It's just going to be another eigenstrain. Like that. Okay? That's a good question. So you have to keep, as I said, the toughest, one of the most difficult thing about these problems is this idea of an eigenstrain that keeps floating around. Because it's, and again, to kind of recover here, review, this is the elastic strain. Because it gets multiplied by the elastic constants, right? So this is Hooke's law. And this is the total strain in here. That's related to gradients in the displacement. Okay, that's pretty important. Okay, questions? Other questions? Okay, so remember when we started our whole discussion of spinodal decomposition, we had a free energy, where this is the free energy density. F is a free energy density, which is a function of composition. Plus k grad c squared. Okay, and I said at the very beginning that the nice thing about phase field models is that you can just add other physics by adding other energies to this free energy functional. And in fact, that's what we're going to do. We're just going to say that the free energy now is an integral of the volume of the chemical energy, but now we're going to add an elastic energy. Which can be a function of the total strain and the composition, and then you have dV, and so you just add another energy term. And the nice thing about that is that we know kind of what to do. We know that you just go ahead, and if you want to, now we need to determine. Okay, so we have this extra energy. We're going to be looking at composition, so composition's conserved. And so in order to understand the mass, remember when we did the mass, the Cahn-Hilliard equation, we said that the mass flux in the system was related to gradients in the generalized chemical potential. And when we derived the generalized chemical potential the last time, we had this term and this term. And now we have to derive the generalized chemical potential when we have this term. And just add them together and you're all set to go. And so we have to look at the first variation of the energy. Oh, I'm sorry, you have to add the constraint. Oh, yep. We want to add the constraint to this. Equals 0. And so you have Ft. The elastic energy. dV. Okay, so we want to set the first variation of the energy equal to 0, and we know how to do all those terms except for this term, the elastic energy. And so I'm just going to concentrate on that one, and you can refer to your notes for the other ones. And so we want to look at the first variation of the elastic energy. So that's going to be equal to and this first variation of the elastic energy with respect to strain is the stress by definition. Is equal to stress is equal to the stress. Is it valid for what materials? Sorry? Hyperelastic. What is a hyperelastic material? Right. And yes, and you get the stress, yes?
That is where we define hyperelastic. Or it is like for any material it is valid. Meaning, can we get stress from the strain energy in all the cases?
Oh, I see. That's an assumption that we're making in this, that there is an elastic energy function, W, the derivative of which gives you the stress. So that's it. That's a by definition.
Happens to be a special case.
Yeah.
There could be other cases where it is still true, but it's not.
That's right. Yeah, exactly. Yeah. Okay. So let's look at these two terms separately here. Let's look at the first term. So we have an integral of Tij, the variation in the strain, dV. And so that's equal to, so you just put in the definition of the displacements. Since Tij is equal to Tji, it's symmetric. This thing becomes J dV. Variation. And you can interchange the variation with the derivative like we did before when we derived the Cahn-Hilliard equation. And use a little trick to take care of this. You know, if you write Tij, take the divergence of that. Okay, so those of you who don't work with additional notation all the time, so let's look at this. Let's look at this term here. So you notice the I is repeated, right? So you're summing from 1 to 3. The only term that's left is J. So this is 3 equations: J1, J2. This is a vector, and you're taking the derivative with respect to the same index. So it's the divergence of a vector, right? So that's just the divergence of a vector. And this is Tij, comma J, variation of Ui plus Tij, comma J. You just pull the derivatives through. And so you'll notice that that's what this is what we have. These two terms are the same. And so you can rewrite that. It's going to be equal to the interval minus dV. So again, I want to stress that this is again the divergence of a vector over a volume, and we know from the divergence theorem it's going to be equal to so if you wrote this in additional notation, it would look like say it again. UI or UJ. There's lots of I's and J's. Oh, I did? Yes, yes. Yes. And so you can see that this last term here, which is a divergence of a vector with respect to index j, we can rewrite this as the integral so that's over the surface, and those are over the volumes. And so these are now independent variations. You you see that the del mu I sits on the outside now, whereas before it was all kind of mixed up together. And I think you can kind of see what's going on here. That this term here, this first term Tij comma j, that's the divergence of the stress tensor, and this is the stress, the normal force along the surface of a sample. Okay, so we'll keep those in mind. And now let's go back and work on this term over here, that last term, involving the derivative of W with respect to E. So we need the So we need the derivative of W, the elastic energy with respect to composition at constant Eij. It's a partial derivative. We know that the elastic energy is 1/2 Tij E. Now let me be careful with the indices here. Okay, so it's 1/2 the 1/2 the elastic stress times the elastic strain, and you can write this as right. So the elastic energy is a scalar, and you can see that these indices work over these two indices over here. So this is in fact a scalar. There's no free indices there. And now you can put in the definition of the elastic strain as the total strain minus the composition generated strain. Right? And so now it's pretty easy to take the derivative with respect to C at constant total strain. Yeah, there's elastic homogeneity. Yeah.
Is not a function of C, even though it can also be.
Yeah. Absolutely. Yeah, that's right. So we're assuming that's yeah. So let's write that. Yeah, that's a constant. Absolutely. And so so the first term disappears because it's a constant, and you get minus eta. Oh, it doesn't disappear. What are you talking about? No, it's still yeah. So you get minus eta delta ij times EKL minus minus eta delta KL EIJ. Oops. Okay. So for the elastic constants have a certain symmetry. Ij. And so remember that even though these terms kind of look, these two terms kind of look independent, they're actually summed. They're actually summing, right? And so since if these two indices are summing over these two indices are summing over these two indices, and it's pretty clear that because this is symmetric and these two terms look exactly the same, except for just changes in the indices, that because of this symmetry, these, after you do the summation without the half, that this term and this term are going to be equal. And so this becomes simply just becomes that. Or you can contract. So this is a delta function, right? And it's 0 if I is not equal to j. So any of the terms that involve ij here that are not identical, where I is not equal to j, will disappear. So you're only interested in the terms when I is equal to j. So you might as well just replace that with j. Yeah, hold on one second. Yeah. CIJKL. IJ, yes.
IJ and K
Or
also can be used, right?
you mean you worry about this one? Yeah, you can do it.
Go back to the, see, W is CIJKL, EIJ, EKL, right? You can take differentiation with respect to IJ or KL. Both of them will give you E. This is related to that energy being symmetric about IJKL. So you are allowed to switch IJ and KL. This is not coming from your. No, it's not coming from that E is symmetric, and so C will have this one. But with IJ and KL as a two people.
Yeah. Yeah. Good question. Yeah. Symmetries of elastic constant tensors. Other questions? Okay. So if you look at this equation down here, you can actually simplify this a bit. Because we know that Tij, the elastic strain times KL, right? That's just the definition. So it implies that Tjj the elastic strain. And we know that the elastic strain is equal to right? That's the total strain minus the eigenstrain. And so if you look at this equation here, that's exactly what I have. And so the W respect to C is just going to be minus eta times the trace of the stress. And that's so. Why is it just the trace of the stress? And it all goes back, really, to this assumption that we have a purely dilatational misfit strain. And so, if we put this all together, we have the first variation of the energy is going to be equal to the terms that we had before, partial F with respect to C, minus K times the Laplacian C. And now we get minus eta Tjj from the elastic energy term. And that's multiplied by delta C. No, I don't want to. Let me put the square brackets here, sorry. And then you have the other terms that I had before. Okay. Yeah. Oh, you meant this, the constraint. Yeah. Yep. Thank you. Yep. No. Sorry. Okay. All right. Other questions? Other questions? Yeah, exactly. Yeah. That's exactly why I wrote it this way, to try to make that connection. Yeah, that's right. And so, to make that equal to 0, if you set this equal to 0, lambda is the partial of f tjj, tij comma j equal to 0, and tij nj equals to 0. This is on the surface of the body. So normally we neglect the surface term here. The surface term is neglected. This is the divergence of the stress tensor, which is this is elastic equilibrium, and so part of this derivation we got elastic equilibrium out of the problem, and this is the chemical equilibrium part. And as just pointed out, the this eigenstrain, or this compositionally generated stresses, just gives you the trace of the stress. If you had a misfit strain, a solute expansion coefficient that was tetragonal, for example, you wouldn't get a trace of the strain. It would be something else. But so Freddie brought up a good point that this kind of looks like a pressure. It's the trace of the stress. But unlike a fluid, this thing can be anisotropic. It can depend upon crystallographic orientation. Okay, and that's one of the things that we want to do now. We want to look at how do you actually get that term. But you can continue to plow along. You say J is equal to minus m gradient lambda. You say that dc dt is equal to the divergence of J, right? And you put that all together, and you get the Cahn-Hilliard equation. Okay, and so you basically pick up the Laplacian of the trace of the stress. You pick up this new term. Okay, so the question here, the question of the hour, is what do you do with the trace of the stress? And the reason why, one of the reasons why I wrote it this way over here, is that you have the trace of the stress. So if you remember, the way I motivated this whole discussion here was I said that I had a composition profile, and that composition profile times the solute expansion coefficient generated stress, right? And so it's clear that if you allow that kind of a picture, it's basically sitting right up there, that this thing here can somehow maybe be written entirely in terms of the composition. And so this whole thing then becomes something times grad squared C, or something like that. So the idea now, so this is general. You don't have to do this. If you had applied stress or some other source of stress, you could use this directly. But what we're going to focus on now is a specific situation where you can replace, where the only source of stress is this non-uniform composition. And so you can kind of almost see, if you take TJJ and you put it back down into here, you're going to get Laplacian in the concentration, which looks a little bit like this. Okay, so. All right, so how do we determine the stress? How do we determine the stress? Well, you go back to the, you have elastic equilibrium, and you substitute the equation I had here, this one, this one, but not contracted, not Tij. You include the total strain and the eigenstrain. So you put that back in. So you substitute it. Oh, let me just do it here. So right. So that's the definition of the strain. So you put this term back into there. You take the derivative, and you end up with an equation that'sCijkl UK, comma, L, JL. So I'm also going to, let me write this out. Do too many steps. Okay, so you write that in terms of gradients and the displacement, and you get that. So minus eta, you get that term over here. Equals 0. And so if you look at this equation here, so C, remember, so C comma J.
Why that minus C naught?
No.
Could be eta C comma J delta K.
No, the C naught shouldn't be there. Right. Sorry. I was thinking one step ahead. Yep. Yep. Thank you. Yeah. So C comma J, so C is a function of x, right? So this is just the partial of C with respect to x, J, right? So C is a function of position. And so what this implies really is that gradients of composition are important. Those are the things that really kind of generate the stress in the problem. So you can write it like this. And the nice thing about these equations is that these are linear equations for UK, but they're coupled. They're clearly coupled by the elastic constants. And they're pretty complicated looking things because they're second derivatives with respect to L and J. So if you actually wrote this equation out, it would be pretty awful. But they're linear equations, right? And since they're linear equations, what does that mean? That means that you can take Fourier transforms. You can take Fourier transforms. And the neat thing about Fourier transforms is that right now this is a partial differential equation in space, right? So let's say JKL. So you have one free index. So these are three equations, right? And you take, let's say, the one component of the displacement, and then you have to take the second derivative with respect to 2, with respect to 3, with respect to 2, with respect to 1. So this is an enormously long, complicated set of equations. And it's a partial differential equation in space. And so remember when we did the diffusion equation, we had the partial squared c with respect to x squared. We took a Fourier transform, and the spatial derivative disappeared and was replaced by kx squared, right? This is the same thing. This just looks a little bit like a Laplacian. It's really not, because it has different indices here. It would be JJ if it was JJ if it was a Laplacian, but it's just indices. And so you take a Fourier transform, and every time you see a derivative, you get k, or ik, actually, ik. And so what's beautiful about Fourier transforms is that you can take this partial differential equation and replace it by a linear set of algebraic equations that just involve wave numbers and these elastic constants. And so that's what's so nice about these Fourier transforms. And
the usual equation that you would get, uk comma nj equal to 0, we just have a
yeah, this one up here.
term on in the final equation.
This one.
Uk comma nj.
Oh yeah, you leave 0.
Delta t equal to 0.
Yeah.
Instead, we just have a term which is on the right hand side.
Yep.
Which is dependent on the eigenstrain.
Yep. That's right.
That is
Yep. Yep. That's right. That's right. So it's an inhomogeneous set of equations, right? It's driven by this term here. You're exactly right. That's right. And so we're going to do Fourier transforms. And so we're going to not worry about boundaries.
oh, but boundary also works fine. If you take Fourier transform.
No, what I mean by this, boundaries at infinity.
Because that dij dot nj, at the two boundaries, they will have opposite. In the previous one, you had
Yeah. This.
dij nj
Yeah.
equal to
Right.
0, because nj will have opposite at plus and minus infinity, for example.
Mm-hmm.
If you have periodic, nj will have plus x and minus x, so they all cancel out.
Yeah. What I mean by that, we're doing things in an infinite domain. We're not doing it in a finite boundary, where we have specific boundary conditions like traction boundary conditions, or traction. Just so we can take Fourier transforms. And so every time a Fourier transform hits a derivative, you get a factor of k. And so let's look at let's just look at a term that looks like this. Try to fix ideas here. So this is the second partial of uk with respect to xl. Right? That's what when you expand that out, right? Okay, so it involves both L, L, and J. And so when you take the Fourier you substitute in the Fourier transform of the displacement. No, let me just do it this way. Take the Fourier transform of that term. Yeah. So again, you integrate by parts, and you'll get minus KL, KJ, the Fourier transform of K. This is in 3 dimensions now. Minus dx. Is that right? No.
Because we want to keep the integral, then it is just
No.
UK.
UK, yeah, that's what I thought. Yeah, the Fourier transform of that. And so, so if you look at if that's basically the term, that sits here. So if you take the Fourier transform of the left-hand side, you get C times the Fourier KL, KJ, the Fourier transform, the amplitude of the Fourier transform, which can be some function of the wave vector k. And you take the Fourier transform of the other side, it's just the composition field. So you'll get so the composition over on this side. So over here you have a composition gradient. So it's replaced by kj times the Fourier transform of the composition. I'm missing the k. Yep. Kj times the Fourier transform of the composition. And so there are no partial derivatives anymore. No partial derivatives. And so if you look at this is again just three equations. I equals 1, 2, and 3. But now they're linear algebraic equations for the three unknowns. The Fourier transform. Okay, so basically it's a linear system of equations. So if you look at the right hand side, so the KL and the KL go together, so that disappears. The J goes to this J, and so you just have I and I. And so they'll set of three equations and three unknowns. And to solve these, you have to use Cramer's rule. When do I supposed to end? Yeah. So it's a linear set. Oh, I see. Okay. Do you have, probably no one remembers this because no one thought it would be actually useful. But you probably did this when you were an undergrad somewhere along the line. So you have a linear system of equations that look like this. So why did I write three equations to three unknowns? That's exactly what we're looking for, right? And in our case, these x's are the u1, u2, u3, the Fourier transforms of those three components. D's on this side is this quantity that Professor Guru just mentioned was basically associated with these three equations. So we want to view this kind of as the known quantity. I give you a Fourier transform of the composition field. That's given, right? You compute that. And then the question is, what kind of strain field or stress field does that generate? And it's related to solving this set of equations. And so you can write down the solution to this equation that looks like this. Okay. And A is the matrix of the coefficients. is the determinant of the coefficients. A is that matrix. And AI is the matrix A with column I replaced by D. And so you can write this immediately out, or AIK in our case. In our case, AIK is basically the coefficient matrix, which is Cij KL KJ. Yep. We look back here. That's those terms, right? And the thing that you do, you can write the determinant of this matrix where you replace the A's with the right with the right hand side as di times nij, where nij is the cofactor matrix. Matrix of Aij. Ij. And so, to give you an illustration of this, if you take the determinant of A1, what you're doing there is you're replacing that first row by the unknown vector, by the known vector on the opposite side. And then what you can do to determine that determinant is that you can rewrite this as D1 times the determinant of the cofactor matrix, which would be you can expand this, the determinant was it D2, so it's B1 times the determinant of the matrix. And so these are what I would call in the cofactor matrices. These are the n's. And so that means that you can write the determinant of AI, in our case, as just delta mk, eta times the Fourier transform, which can be some function of the wave number. That's the term you get from the derivative. And here are the cofactors. And so now you get an expression for, so the nice thing about this is that it allows you to write directly the answer that you get. You get the A, and you could write this finally as where omega ij is determinant of the matrix.
So the left-hand side should be UI.
It should be ui. Okay, so now we have the Fourier transform of the displacement field, and we basically have everything we need. Because now that we have this Fourier transform, we know that, we can write the displacement gradient in terms of the stresses in terms of Fourier transforms of the displacement. And so you can immediately begin to get the stresses and the strains out of the problem. So let's see. So you could write the stresses exactly in terms of the Fourier transforms. So we had after much algebra, and my apologies for this being a little technical. This is probably the most technical stuff that we will do in the class. We have an expression for the Fourier transform of the displacement field, and that means that we can go back and determine the stress field, KL, and you can substitute and see dx. So we can substitute those things into that equation. Put these two, put this in here, take a derivative, so you just get a KL, and this term into here.
Those integrals should be over
dk. Yes. Yes, dk. Yeah. And substitute those into there. And so and so after you make the substitution, so we'll get an IKL from the derivative. And then from the composition term, you have the solute expansion coefficient, the Fourier transform of the composition field. You don't have a derivative here, so you just have e to the ikx. dk. And now you substitute in the expression that we have for u tilde, which is here. So you substitute that in. And this thing becomes quite long. So the I here, and the I here become -1. That cancels the minus sign. That cancels, yeah, the minus sign that's here. Okay, there's supposed to be a minus sign there. Sorry, correction. That's put a minus sign in your notes there. It should be -1. So it cancels the minus sign there, and you get Okay. And so you can write the stress now as the integral of C, J, N, M, M, K, L, K, N, omega, K, J, minus eta, okay. So let me see if I did the KJ, J, M, 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 KJ. Yep. So if you look at this term, there's KJ, a KL, and that's KL, that's eta. And there's supposed to be an eta in there too, like that. And so if you look at this, expression here, this is very nice. And says what it says is here's the prescription. So this thing is a complicated mess, right? I mean, you have to determine this omega, which involves these cofactors and all the rest of the stuff. It's kind of messy. You can look this up in books, in Toshio Mura's book or Khachaturian's book, for example, will have these expressions for these things for various symmetries. But the important point here is that this is all fixed. Once you fix the crystallographic anisotropy in this system, this is all fixed. And to determine the stress, all you need to do is to determine the Fourier transform of the composition profile and take this basically inverse Fourier transform to get this. Okay? And so it's very fast. So if you think about a composition that's evolving in time, you're doing a phase field method, this is the only thing that's evolving in time. This doesn't change. So you compute that once and for all, and you're kind of done. And you're just doing these integrals of Fourier space, which you would think would be pretty hard, but they're pretty easy if you use fast Fourier transforms. So it goes pretty quickly. So that's how to get the stress. And as promised, I'm going to give you just a few more minutes here so that you can get back to your exercises. But let's go back to the Cahn-Hilliard equation. The Cahn-Hilliard equation. And so that's what the Cahn-Hilliard equation looks like in additional Cartesian coordinates and additional coordinates. And we kind of know what happens to when we write the Fourier transform of this out. I think what's clear is that this thing here is nonlinear, so you can't take the Fourier transform of that. And so we're going to do another problem. We're going to assume that f is going to be replaced by f double prime at some c0. So we're going to look at the stability about c0. And we kind of know what happens to all the rest of the term. So if this is a constant here, you just get a k squared term here. This is a constant k. It doesn't depend upon composition. You just get a k to the fourth term there. The only thing that's a little different is this one. And let me talk about the Fourier transform of that. So you have t, which is a function of position. Fourier transform is a function of k. dk. It's a vector. So TRS comma II dk. And so you can then substitute in what the Fourier transform of the stress is, and it's just basically that term that I had. Fourier transform of the stress is basically, you notice that here, this thing is e to the ikx, so the Fourier transform of the stress is all of this stuff, basically all related to all of that stuff. Minus k squared c 0I. And see, the key here is you notice what's happening beyond all the algebra is that basically what we're at the goal. Remember, I motivated this by saying it would be really great if I could write this thing entirely in terms of the concentration. And if I could do that, then I have something that's only functions of concentration on the right-hand side, and you get rid of the stress. And that's in fact, what we can do if we use the Fourier transform. So we end up with the Fourier transform of the composition after all this work. Okay. And so I'm going to simplify the algebra a little bit. We're only interested in the trace of the Laplacian of the trace of the stress. And so I'm going to write this as the Fourier transform of the composition field. And this function b is a function of k only depends upon the wave vectors. So it's basically all of that. As I said before, once you fix the composition in the system, once you fix the crystallography, that's all you have left. And so you can immediately put this all back into the equations for the Fourier transform, and you say that C is equal to e to the you have the amplification factor again. So you can write the equation for the evolution of just exactly like we did before, where we have the second derivative of the molar free volume. Now this is a constant evaluated at the composition. We have this bk function. We're taking the Laplacian of the stress, therefore you just get a k squared c tilde. And so that means that the amplification factor is just minus m. Plus k to the fourth. Okay, so the important point here is that the amplification factor Q now depends on the crystallography. Okay? So the amplification factor depends upon the crystallographic direction, because it's basically, if you look at what this B is, it's a complicated function of all of these elastic constants and the cofactor matrix up here. And but it depends upon crystallographic orientation. And so this is kind of an interesting thing in that you have a diffusion equation where M, the mobility, is isotropic, but B can be anisotropic. And in fact, in a cubic system, B can be anisotropic. And so if you think about diffusion in a cubic system, you probably learned that the diffusion constant has to be isotropic because it's cubic. But because of the elasticity, it can be anisotropic. And so the elastic energy of the system here is affecting basically the dynamics of the fluctuation spectrum. And so to figure out how anisotropic this is, you simply have to evaluate B as a function of K, and believe me, I'm not going to go through that. No way. No way. But it's a fairly complicated object. So I'm just going to kind of hit the highlights here of what happens. So if Q is positive, it grows. So there's a minus sign out here, which means if this is negative, the system's going to be unstable with respect to composition fluctuations, right? So that means that if f double prime plus 2 eta squared b has to be less than 0. And if you want this condition to hold for all k, you have to at least have f double prime plus 2 eta squared b be less than 0. Okay? And so why is this an interesting result? Remember when we did the spinodal decomposition case, we say it was unstable if f double prime is less than 0. But now we can find cases if b can be greater than 0, then it's possible for the system to be stable. Even though f double prime is less than 0. Okay? And so what does that mean in the phase diagram? So I said, when I drew this out, I said this was the spinodal when we started this journey together. And this is where f double prime is less than 0. And I said, okay, f double prime less than 0, the system's unstable. But now we find if you put in elasticity, that the condition is not f double prime less than 0, but it's this whole thing less than 0, which means that if there are certain crystallographic directions where B is positive, the actual thing, the limit of metastability, is displaced. And this is called a coherent spinodal. Okay? So what it means is that you can actually take a material and quench it below the phase diagram given by CalFad, where you assume the system is stress-free, and it won't phase separate. It'll happily sit there. Okay? And if eta is, if you look at aluminum, platinum, if eta is 0.038, So this is the strain due to composition variations. This difference here is 200 degrees centigrade. This is a non-negligible contribution. If you look at aluminum, silver, nickel, where 8 is much bigger, T minus T sub C is going to be equal to 2,000 C. So basically, the elastic energy cost of generating composition fluctuations is so big that you never get basically never get spinodal decomposition.
Then you can see this spinodal flowing outside the system.
So B of K can be anisotropic, and I can write out the equation for you, but it's actually in the Hilliard article that Guru sent you. That it's in that article. But what that means is that you have something that can be even stranger, where you have the miscibility gap here. This is the incoherent spinodal. And then you get spinodal temperatures that depend on the direction of the fluctuation. So this would be for fluctuations along the 100 directions of the crystal in a cubic material. Most cubic materials, and you can have another one that's down here for 111. And so these are the elastically soft directions. For example, in something like copper, and this is elastically hard. Something like copper, okay? And so you can get spinodals that depend upon the crystallographic direction. And so if you run your code with this kind of anisotropy, instead of getting these worm-like structures I showed you before, what you do is you get fluctuations that go along the elastically soft directions of the crystal. And so instead of getting these kind of wormy-like structures that I showed you in the pictures, you get structures that look like more like. Yeah, so it depends upon the ratio of that quantity. It's kind of the anisotropy factor for a cubic crystal. And so this is the shear modulus. This is a shear modulus along the another crystal 110 direction, and that's another elastic constant. So this combination tells you what direction it is. And so it's possible, for example, I think molybdenum is one where this is inverted. So this becomes 111 and that becomes 100. I think Guru probably knows that. So I looked those elastic constants up in a book. Yeah. So 111, that's right. So 111 is the close packed. The atoms are closer together. They sit closer to the bottoms of their energy well, so you'd expect it to be the energy to strain those atoms along the 111 would be higher than the 100 when they're farther separated. And that's true in 90% of the crystals except for a couple. Yeah, that's right. And so you end up with these highly anisotropic-like structures. And it's entirely built in to this model through B. So here I can write out what B is if you're interested, just so that you know, just so that for a cubic crystal it's and I've given you all the information you need to determine this. You just have to sit down and do lots of algebra. So if you look at the Hilliard's article, he evaluated this for very specific directions. The approach I just gave you there will give you for all directions. But you can see that you have this anisotropy factor here, which can change. This can change sign, so it can change the anisotropy with respect to fluctuations. So if you wanted to look at a 111 direction, this would be 111. A 100 direction, that would be 1, and all the rest would be 0. And so you can see how those would change. They basically weight this anisotropy factor differently, and that's what gives you the anisotropy in the system. Okay, questions? Okay. All right, okay. Sounds good. We'll see you tomorrow then.